All right, kids, it's Wednesday, and we've got to get through this whole lecture on all these three random equations that are up here that look completely different, but yet they're all very similar, and they're all related to each other. So we're going to start with this one. This is going to get you what's called your pressure based upon your depth. So this is the initial pressure, this is rho GH. This is your density times G times H. So like for example, we'll go through this and say, okay, here's this beaker of water. So P naught is going to be the pressure that's at the top of this. And then you've got rho, which is the density of the water. And then you have G, you know what that is, and H is going to be like how far below you are the surface. So what this means is that the deeper that you go, the more pressure that you're going to have. So if you've ever like swam, and I'm guessing Lauren or all of you that have swam except for Adeline, when you dive down into a deeper water, that pressure gets greater and greater and greater. Okay? So that's going to be the first one. Then you've got this one, which is what's known as the continuity equation. This is the longest equation that you will ever see on any of the sheets, AP Physics 1 or AP Physics 2. And we'll get through all of this. And then this relates to cross-sectional area and velocity and how fast water is moving. So we're going to kind of work our way through all three of these. So let's start with that first one. So if you look at the units don't look like they work out to be the same, but they do because this is newtons per square meter. And if you take density times G times H, you do end up with the same units that you do with this P naught, because obviously that's the only way that you can add them together. So the kind of a cool way to view this is that I've got this manifold. So what I'm going to do is I'm going to pour this fluid here into this, okay? So I've got this big wide one here. I've got kind of this snaky looking one here, and then I've got one that has this bulb, right? And then this one is just this long skinny one here. So what I'm going to do is I'm going to pour that fluid into this one. And then that will allow that to flow over here and then up these. So here's the question, okay? And if you were all here, I'd have you vote on this. But when I pour this in, what do you think is going to happen to the height going across here? So let's say that I get this water level up to here on this one. So the question is, what's going to happen to the height of these? Are they going to be the same? Is this one going to be less because it's going to fill up this reservoir here and then maybe that won't be as high? This one has this crooked one. Maybe that's going to throw a kink in it. Maybe it won't. That's going to make it harder for that fluid to go up. Maybe that's going to happen. This one's just smaller, so maybe that one might be the same height. Okay? So those are some considerations. So I'm going to take this and I'm just going to pour this in here. Okay. So here's the deal. So when you look at this, you'll notice that the level is the same across all three of these. So here's the reason why. When you look at this calculation with this equation right here, notice that the cross-sectional area of the tube doesn't make any difference. So what that means is that all of these are going to have the same P naught because they all have the same atmospheric pressure across all three of these. So P naught is going to be the same. So if I come down here, right, at a certain depth, okay, maybe 0.05 meters, 5 centimeters. So what that means is as I go across here, okay, they're all going to have the same pressure across here. It's all going to be the same. Even down here at the bottom, the pressure is going to be the same. So even though like this one has this bigger cross-sectional area at the top, when you look at what is going to be a factor in this equation, they're all the exact same. Okay? They are all the exact same. So no matter where I am in this column, the pressure is going to be the same. Now, here's another thing that you can do. So I'm going to take this, I'm going to set this aside. So then I have literally a U-tube, okay? Not what you watched on the videos, but actually this is a U-shaped tube. It's called a U-tube. So I'm going to take some of this water, I'm going to pour it in. Okay. Now, you'll notice that the water level is the same. Okay? So, if I'm here, if you look at this equation, if I'm up here at the top, the pressure here is just going to be my atmospheric pressure. As I go down, okay, across like this, right? If I go to a certain depth down here, the pressure is going to be the same here as it is on this side. Now, I'm going to blow a little bit of pressure on this side. Okay, hopefully I don't blow this. Hold on. Now, you'll notice that when I was blowing, I was exhaling. So when I was pushing down on this side by blowing on this side, notice that I caused that column to go up. So as I was increasing the pressure here, there was more particles of nitrogen and oxygen, a little carbon dioxide, that were pushing down here, so it pushed that side up. But here's what's important. Even when I got down here, that pressure there is going to be the exact same as that pressure over there, okay, as long as it's the same depth. Now, an added degree of technical difficulty, take this, put this in here, and now I'm going to add some cooking oil to this. Okay, so this is just your basic pure canola oil. So I'm going to pour some on here. Okay. Now, an interesting thing happens. It's a very interesting thing. So first off, you'll notice that you have an interface right here, okay, where these two liquids aren't mixing. The golden rule of fluids is that likes dissolve likes. So this oil has a completely different polarity than the water does. The oil is actually composed of like neutral atoms. The water actually has a dipole moment. If you take AP chemistry, we'll get into that. So these things don't mix because they don't like each other. Now, here's what's important. So when you look at this tube, okay, like this. And so here's the water, there's the oil, okay? So that's oil, and then this is water over here, okay? So here's the deal. This pressure at this point, if you go across like this, is exactly the same, okay? So the pressure down here is the exact same here as it is there, because it's the same depth. Now, here's the kicker. Notice that the oil is higher than the water is. Now, here's the reason why. The oil is less dense. That's why it floats on top of that water. So, if you look at rho G H, so the oil on this side has a slightly lower density than the water does. So over here, so this water here, column, is a little bit more dense. So these two pressures, okay, right here, are the exact same. So I've got to have a taller column of oil over here because it has a slightly less density. So to get that pressure up above it, the water side is more dense. So over here with that water side, that's going to be a bigger rho times G, so it has a smaller H. Over here on the oil side, that has a smaller density, same G, so that has to have a bigger height, because that pressure is going to be the same going across here. Now, notice again, I didn't factor in the size of this tube. Doesn't matter, okay? Does not matter. So like if I want to find the pressure right here, okay, at this point, I would take the atmospheric pressure, P naught, plus rho GH. So I would take P naught, which whatever our atmospheric pressure is, probably around 101,300 pascals, times the density of the oil times G times that height. And that would equal the same thing over here. Both have the same P naught. This has a slightly bigger density, therefore I don't have to have as much height to create that same pressure at both points across here. Okay, so we got that one. All right, so let me put this over here. So let's go to the continuity equation. Now, like I said, this is the longest equation that exists in this class. So let me kind of take you through this. And you wouldn't think they have the same units, but they do. So this is pressure 1, pressure 2. This is rho g y1, so this is the same thing right here, rho g y1. Instead of rho gh, you put it as rho g y1. Now, this is 1/2, and this is density times velocity squared. So if you look at the units, that density is kilograms per cubic meter. And then you have velocity squared, which is meters squared over second squared. Okay? So if you look at the rho GH part of this part up here, so that's kilograms per cubic meter times meters per second squared times meters. So notice up here, you get meters squared over second squared over cubic meters over kilograms, which is the exact same thing you get here. So all three of these, they look completely different, but they all end up with the same units of newtons per square meter. So they're all the exact same. So let me kind of give you some simple examples of how this plays out. So, I go get a ping pong ball. Hold on, give me 1 second. I knew I was doing something. All right. So here's the deal. So I'm going to take this ping pong ball, I'm going to put it in here, right? And if I just let go of it, oddly enough, it falls. But if I blow down, and I'm going to be blowing down, okay? I'm not going to be sucking up, I'm going to be blowing down. Now, your intuition would say, oh, when Burkamp blows down, there's going to be downward pressure on the ping pong ball, and it should even fall faster because of the fact that we're exerting this downward force. But look what happens. So if I blow hard enough, okay, a couple of things happen. Number one, notice how that ping pong ball begins to spin. So we're applying a torque to it. The other thing that happens, again, if I just let go of it, it falls. But if I blow really fast, it actually hovers within that cone. So what's happening, oddly enough, is this. And this is, you'll see, this is why airplanes fly. So here's what you want to look at, is that the faster the faster air moves, the lower the pressure is, okay? So just keep that in mind. So let's say that I'm going to take this piece of paper, like this, okay? And I'm going to hold it just like this, and then I'm going to blow over the top of it, okay? Now, when I blow over the top of it, I want you to watch what happens. Now, when I blow over the top of it, notice that that paper lifts up. So what's happening is, if you look at this continuity equation, and when I blow across that paper, here's what's happening. This is going to be some pressure, this is going to be some pressure. Now, I'm not going to worry about the rho g y parts of it. This is when you have like a difference in like depth based upon like a pipe being underground. So I'm not going to worry about this part of it. All I'm going to worry about is the two pressures. So here's the deal. So I'm not going to worry about that. I'm not going to worry about that. So what I'm going to look at, let me get all that gone, is that I'm going to have P1 plus 1/2 rho G1 squared, rho, screw that up, equals P2 plus 1/2 rho G V2 squared. Okay, so here's the deal. So things lift because of a pressure differential. Planes fly because of a pressure differential. So what's happening is that when I just hold this paper like this, the pressure is the same on both sides of the paper. So when I blow across the top of this, the only way that paper lift up is if there's more pressure on the bottom than there is on the top. So what's happening is that when I blow across the top, okay, this velocity side over here is getting bigger. So there's no velocity on this side, but when I blow across on the top of the paper, now I have a velocity. So this velocity is bigger. So this makes this part of the equation big. So the only way that can happen, because of the fact that there's an don't dismiss the significance of this equal sign. So P1's here. I don't have to worry about this part of it because there is no initial velocity. So when I blow across the top of it over here, this part becomes bigger. So the only way that can happen is if this gets bigger, that means P2 has to drop. So mathematically what's happening is this. So here's that sheet of paper. So when I blow across the top of it, that's creating a low pressure. If you want to think of it this way, when I blow across the top, there aren't as many nitrogen and oxygen molecules coming in contact with this side of the paper. So it's kind of like what we did with the tube, and we had, I don't know, Fullerton and Josh, I think, Brady, yeah, okay, and they were hitting on Ryan, and they were hitting, on both sides. So basically what we're doing is that we're decreasing the number of particles that are colliding on this side because I'm making them to go this way. But I have the same number of particles that are pushing on this side, so that's what makes this thing lift up. So here's what I want you to see. The faster air moves, the lower the pressure. So to balance this out, okay, this goes away. I've got a big value here, so that creates a low pressure here. So that's what's happening when I take this and I blow across here, like this. So what's happening is that as that air is going around that ping pong ball, is creating a low pressure system because I don't have as much nitrogen and oxygen molecules colliding with this side of it. But I have the same number of particles that are colliding on this side. So therefore, I create a pressure differential, and it isn't being sucked up, it's actually being pushed up because I have a smaller number of collisions on the top than I have on the bottom, and that difference is enough to make that happen. Now, if I don't blow fast enough, okay, so if I just kind of put a weak effort into it, nothing happens. But if I go fast enough, hold on, I'm getting tired. If I go fast enough, then it seems to defy gravity. But because again, that pushing up is faster, so it's creating a greater pressure because I have low pressure here, I have a pressure differential that's pushing it up, and it goes. All right, now, so I'm going to forget about this equation for just a second. We're going to get back to it. So the other one is A1 V1 equaling A2 V2. Okay, so again, this is on this purple sheet right here. Now, this is area. This is velocity. Now, this is a situation that you all have used this equation. You just don't know that you've used this equation before. So if you've ever held, like here's a garden hose, right? And you have the water coming out. So if you look at what happens, you want to spray this out. Oh, right? You take your thumb and you put it over that opening. So once you put that over the opening, that water goes faster. Now, if you look at the units, okay? So you have a cross-sectional area which is in meters squared. So if this was like a hose, a round hose, that would be pi r squared. Then I've got a velocity in meters per second. So here's what's important. This is cubic meters per second. So this is volume per unit of time. So if you look at what is happening with this hose. So imagine that you have a slug of water. Okay? Here's this slug of water moving at a certain velocity. So this is cubic meters per second. So I have a certain volume of water here that's moving through this hose. Okay? Certain volume of water per unit of time. Now, when it gets here, I have to have that same volume of water moving through, okay? Because the water can't be compressed. So, to get that same volume of water going through that smaller opening, so I have to make it go faster. So, I'm decreasing the volume, the cross-sectional area, okay? So to compensate for that, it has to go faster. Again, because there is an equal sign. So if you look at what's happening with a hose, right? So here's your water. You put your thumb over it, okay? So you have area 1, velocity 1 equals area 2, velocity 2. So that would be pi r. Now, when it's in the hose, you've got a big radius that gets squared times a small velocity. Now, when you put your thumb over the end of it, then that's going to be pi, but then you've got a smaller radius squared. To make up for that, then you have to have a larger velocity. So, now, look at what happens here. As long as it's a cross-sectional area of like a pipe or a hose or a circle, notice that these pi's actually cancel out. So if you look at this in terms of like a ratio, it's a ratio of radius squareds because of the fact that you're talking cross-sectional area. So if they're both round, you don't have to worry about the pi's, just look at it in terms of a ratio of r squareds. So keep in mind, that's r squared. So let's say, for example, here's the situation. Again, I'll use this syringe. So I'm going to take this syringe, I'm going to draw up some fluid, okay? Get the air pocket out of there. So if you look at what happens with this syringe, so when I push this out, okay, so I'm going to push this plunger really slowly, okay? And let's say that this cross-sectional area, let's say that radius is 1 centimeter, okay? So that radius is 1 centimeter. Now, then it's going to come out this end of the nozzle, which is really, 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 really small, okay? So let's say that's like 2 millimeters, which would be, so let's say that radius there is 0.01 meters, okay, which would be like 1 millimeter. No, I'm sorry. Hold on. It would be 0.001 meters. And let's make that 0.01 meters. Okay, so that way we're in meters. So this radius is 10 centimeters. Excuse me, is 1 centimeter, okay? This kind of ballpark in that's about 1 centimeter. Then that radius there is about 1 millimeter, which would be 0.001 meters. So let's say that when I push the syringe like this, let's say I'm pushing that really, really slowly at about 2 centimeters per second, which would be about 0.02 meters per second. So I'm going to push this at 2 centimeters per second, okay, which would be about like that. So what I want to figure out is how fast the fluid is going to be coming out over there. So I'm going to take 0.02 meters per second times pi times 0.01 meters squared. And then I'm going to have that new velocity that I don't know, okay? So that's what I'm searching for, is that new velocity. And then that's going to be pi times 0.001 meters squared. So again, the pi's are going to cancel out, okay? All right? So then if you do a little bit of math, so give me a second here, all right? So I'm going to take, okay, then I'm going to divide that by and then so then that velocity works out to be 2 meters per second. So here's the deal. So this is moving really slow at 0.02 meters per second. The velocity of the liquid coming out is going to be 2 meters per second. So here's what I want you to see. I got a big cross-sectional area here that's moving slow. Here I've got a small cross-sectional area moving fast. So this is why when I take this syringe, and this is why I wish some of you were here in this room, I'd shoot this at you. So if you look, I don't know, hopefully you can see this. So when I do that, and I guarantee, so to give you some perspective, either Kelsey Thurman or Josh Avery, if they were sitting there in their normal chairs, I guarantee you I would have gotten them wet, okay? Because that's how far that fluid would have gone. So, by the way, that problems like that lends itself towards projectile motion problems. So I could say, hey, I'm on top of a mountain. I'm going to take this fluid, okay, and I'm on top of a mountain. I'm going to push it with a certain velocity here, calculate the exit velocity, and then figure out how far that's going to go. So I could take that equation and tie it in with this. Okay, so here's where this all plays out in terms of this continuity equation. So if you look at like how water systems work, so water lines are buried below the ground. So what happens here is that if you look at P plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. So here's kind of the cool thing about this. This is like the potential energy part of it, because of the fact that you're talking about like how high something is. This is the kinetic energy part of it. So you have basically a pressure part, a potential energy part, and a kinetic energy part. So you have pressure, potential, kinetic energy. But they're all in newtons per square meter, but that's kind of the basic concept of this. So if you look at what happens in terms of this equation, if you're clever, and you are, you're going to let rho g y1, you're going to let this lower depth of where this water is below the ground, you're going to let that be equal to 0. Okay, so that's going to go away. Now, what happens is that you have a big cross-sectional area here coming up to a small opening here, like, you know, like the drinking fountains or the faucet in your house, okay? That's a pretty small opening, but you've got a big pipe down here. So, look what happens. So, first off, and this is why you look at this in its entirety. Here you have a big cross-sectional area of this water that's moving. And then you shrink it down to a smaller opening. So what we just showed is that down here, that water is moving slow. But here, it's moving fast because of the fact that you have a smaller opening here. So you've got slow water here, fast water here. Okay? Now, look what happens. So I'm going to let this go to 0, so this is going to be P1 plus 1/2 rho, and this thing is that down below it's going to be moving pretty slow. So I'm going to have this be a smaller value. Now, this is going to be P2 plus rho G Y2 plus 1/2 rho. Now, here's the deal. Don't forget about this equal sign right here, okay? So this is important. There's an equal sign right here. So these two sides have to add up to equal to 0. So down here, you're going to have a small velocity, so you're going to have a big pressure. So what happens over here, and I'm going to talk about this V right away, because we know that velocity over there has to be bigger than this velocity here because of the fact that it's a smaller opening. So this is going to be V2 squared. So this velocity here is going to be bigger than this velocity here. Now, look what happens. Now I've got this non-zero value here because now this is going to be this height. Oh, how far does that water have to move up? Okay, so this is now a bigger value. This is now a bigger value. So the only way that this can equal out is if this is going to have a lower pressure. So what happens is this. Down below, you have a high pressure system. This water is under a lot of pressure, but it's moving really slow. Then when it comes out, you have a lower pressure because you have to push it up the hill, but it's going to be moving faster, okay? So if you just look at this in terms of continuity equation. Now, you also have what's called gauge pressure and absolute pressure. Gauge pressure is basically already taking into account the atmospheric pressure that you have. So typically when you, like for example, when you look at the tire pressure gauge to check the pressure on your tires, this is what we call gauge pressure. Because technically, that pressure is already calibrated for 1 atmospheric pressure. So when you take that and you put that on the valve stem of your tires, and it's going to read like 35 psi, okay, whatever that is. That's already taken into account the fact that we already have 1 atmospheric pressure. So that's already being taken into account because, so gauge pressure is already taken into the fact that we exist under 1 atmospheric pressure. So sometimes you see that being a difference. Okay, kids, I'm done. So what's going to happen is that this last assignment is not due. I'm going to send out the answer key with this lecture. It would very much behoove you to get a feel for these equations, okay, so that you know how they play out. They're not difficult if you understand the concept of them. So hopefully with all the demos that I did, you get a feel for what's going to happen in terms of the conceptual part of these equations. So, peace out, kids.